Assalamualaikum. I would like to present 7.4 isentropic processes. As previous group has mentioned, entropy of a fixed mass can be changed by heat transfer and irreversibilities. Then it follows by entropy of a fixed mass does not change during process that is internally reversible and adiabatic. But isentropic processes is a process during which entropy remains constant. It is characterized by this formula delta S equals to 0, which is constant, or S2 equals to S1. And this is the unit for the processes. The formula is derived from the reversible adiabatic processes and comes out the formula. From the formula, we know that the isentropic processes is the process which the entropy value in the beginning remains constant to the end of the processes. As in the diagram, we can see that during internally reversible adiabatic process, the entropy remains constant. And from the graph, we can see that it appears as a vertical line as the entropy is constant.
So let's take a look at example 7.5. Steam enters an adiabatic turbine at 5 megapascal and 450 degrees Celsius and leaves at a pressure of 1.4 megapascal. Determine the work output of the turbine per unit mass of steam if the process is reversible. So at step 1, we can get from the question the process is adiabatic and reversible. So S1 is equals to S2. This process is isentropic, and because the process is adiabatic, there is no heat transfer, so Q is equals to 0. And then we can use the formula of E in minus E out equals to 0 because this process is a steady state flow. So rearrange E in is equals to E out, and then we change it to work equals to mass flow rate times H1 minus H2. But the question wants the work output of the turbine per unit mass. So the work per unit mass is equals to H1 minus H2. At step number 2, we can see that at state 1, P equal 5 megapascal and temperature equals 450 degrees Celsius. And then from table A6, we can get the value of H1 and S1. Next, at step 3, we know that S1 is equals to S2. So we use the formula S2 equals to SF plus X2 SFG. We can get the value of SF and SFG from table A5 and then insert the value, so we can get the X2. After we get the X2, we can find H2 by using formula H2 equal HF plus X2 HFG. So we can get the value of HF and HFG at table A5 at pressure equal 1.4 megapascal. So if we insert the value, we will get the value of H2 is equal to 2953.41 kilojoule per kg. And then we insert the value of H1 and H2 inside the work formula, and we will get 363.79 kilojoule per kg.
Property diagrams serve a great visual aid in the thermodynamic analysis of processes. We have used PV and PV diagram extensively in previous chapters in conjunction with the first law of thermodynamics. In the second law analysis, it is very helpful to plot the processes on diagram for which one of the coordinates is entropy. The two diagrams commonly used in the second law analysis are the temperature entropy and the enthalpy entropy diagrams. So recall that ds is equal to delta Q over T internally reversible. So internally reversible process is we got the delta Q over T, we will be getting the ds, which mean delta Q internally reversible is equal to TdS. Also means that Q internally reversible is equal equal to the integral of TdS. So we've seen this kind of form in PDV integral, and it happened to do the reversible work done by the system by using the area under the graph. So same goes to TS diagram, and because all of the diagram that we plot are inherently internally reversible, since we cannot plot irreversible process on 2D diagram, so most of the diagram that we plot are internally reversible. We can calculate the heat for the process using TS diagram like this. TS diagram. First we draw the graph and we label it TS, and let's say we have two phase from phase 1 to phase 2, and the area under the curve would be the Q, and the Q is equal to the integral of TdS from range 1 to 2. How about isothermal expansion? Let's say we have the state from 3 to 4. So the process along this path would be expressed with the equation of Q is equal to integral from 3 to 4 T ds also. But since the T is constant, we can just like take it out to be T S4 minus S3 like that.
Hi everyone, I'm FARISHA and I'm going to explain example 7.6 from the textbook, the TS diagram of the Carnot cycle. So the question asks us to show the Carnot cycle on the TS diagram and indicate the areas that represent the heat supplied QH, heat rejected QL, and the net work output W net out. If we look back at chapter 5, we know that Carnot cycle is made out of 4 processes, which are reversible isothermal expansion, reversible adiabatic expansion, reversible isothermal compression, and also reversible adiabatic compression. So, reversible isothermal expansion is a process from 1 to 2, where the TH is constant, while reversible adiabatic expansion is a process from point 2 to 3, where the temperature drops from TH to TL. The next process is reversible isothermal compression, where the process moves from 3 to 4 and the TL is constant. And the last process in Carnot cycle is reversible adiabatic compression, where the process is from 4 to point 1, where the temperature rises from TL to TH. Therefore, these 4 processes of Carnot cycle form a rectangular on a TS diagram. So as we know in TS diagram, the area under the graph is equals to Q, or heat. Therefore, the area of A1, 2 to B is the QH, which is the heat supplied. And for the heat rejected QL is the area from A, 4, 3, and B, right here. So to obtain the work net output, we use the formula work net output equals to QH minus QL, which we have obtained from the area under the graph.
So what is entropy? Entropy can be viewed as a measure of molecular disorder or molecular randomness. As the system becomes more disordered, the positions of molecules become less predictable and the entropy increases. Therefore, the entropy of a substance is lowest in the solid phase and highest in the gas phase. In the solid phase, the molecules of a substance continually oscillate about their equilibrium positions, but they cannot move relative to each other, and their position at any instant can be predicted with good certainty. While in the gas phase, the molecules move about at random, collide with each other, and change direction, making it extremely difficult to predict accurately in the microscopic state of a system at any instant. So this is the Boltzmann relation, which shows that the entropy equals to Boltzmann constant ln probability. So the next is third law of thermodynamics. The third law of thermodynamics states that the entropy of a pure crystalline substance at absolute zero temperature is zero, since there is no uncertainty about the state of molecules at that instant. The third law of thermodynamics provides an absolute reference point for the determination of entropy, and the entropy determined relative to this point is called absolute entropy. The entropy of a solid solution is not zero at absolute zero temperature, because more than one molecular configuration exists for such substances, which introduce some uncertainty about the microscopic state of substance. Next, heat is a form of disorganized energy, and some disorganization, which is entropy, flows with heat. As a result, the entropy and the level of molecular disorder or randomness of the hot body decreases, with the entropy and the level of molecular disorder of the cold body increases. During a heat transfer process, the net entropy increases, which means the increase in the entropy of the cold body more than offsets the decrease in the entropy of the hot body. The combined system, which refers to hot body and the cold body, is at a state of great disorder at the final state. Thus, we can conclude that the processes can occur only in the direction of increased overall entropy or molecular disorder.